All right, today we're going deep. We're diving right into the heart of the atom to take a look at its tiny, dense, and unbelievably powerful core, the nucleus.
And right away, we run into a huge puzzle. I mean, think about it. The nucleus is stuffed with particles that are all positively charged. Basic physics tells us they should be pushing each other apart with incredible force. So, what in the world is holding it all together? That's the big mystery we're going to solve.
Okay, to crack this case, first we need to get to know the key players, the main characters inside that tiny core. So here they are. You've got your proton, which carries a positive charge. And then you have the neutron, which, as the name suggests, is totally neutral. But here's the really important part. Check out their mass. They're almost identical, and they are both way heavier than the electrons zipping around on the outside.
You know, to make things a little easier, scientists came up with a handy nickname for both protons and neutrons. They just call them nucleons. It's a great shorthand, so we're going to use that from now on when we talk about everything packed inside the nucleus.
And that just brings us right back to the million-dollar question. We've got all these positive protons crammed into a ridiculously small space. The repulsion between them should be enormous. It's kind of like trying to force the positive ends of a dozen super strong magnets together in a little box. It just shouldn't work. So, what's the secret?
Well, the first clue is a real head-scratcher. It's totally counterintuitive, and it's not about what's there, but about what seems to be missing. This is where things get really interesting.
And no, that's not a typo. You heard that right. If you were to weigh all the individual protons and neutrons separately and then weigh the nucleus they form when they come together, the final nucleus actually weighs a little bit less. It's a bizarre phenomenon, but it's the key to this entire mystery.
This weird difference in weight has a name. It's called the mass defect. It's that literal, measurable amount of mass that seems to vanish when the parts become a whole. Which, of course, leads to the big question.
I mean, it can't just disappear, right? Basic laws of physics say you can't just create or destroy mass. So where did it go? This is the absolute heart of the matter.
And the answer comes from probably the most famous equation ever, E equals mc squared. That missing mass from the mass defect wasn't lost at all. It was converted into a tremendous amount of energy. This is what's called binding energy, and it acts like the universe's strongest superglue, holding all those nucleons together, whether they like it or not. Okay, so if this binding energy is the secret to keeping a nucleus stable, how does it change from element to element? Is there a pattern? Well, for that, we need a map. And what we're about to look at is arguably the single most important chart in all of nuclear physics. This right here is the binding energy curve. It's pretty simple to read. Along the bottom, you have the number of nucleons, basically how heavy the element is. And on the side, you have how much binding energy is holding each one of those nucleons in place. So just think of it as a stability map. The higher an element is on this curve, the more stable its nucleus is.
And this curve tells an amazing story. You see how on the left, for the light elements, the curve just shoots upward. Then it hits this peak, this absolute summit of stability right at iron 56. That's it, the most stable nucleus in the whole universe. But after iron, as the nuclei get heavier and heavier, they actually become a little less stable, and you see the curve start to slowly slope back down. And that shape, that curve, is exactly why there are two main ways to get energy out of atoms. You can take light elements from the left side and combine them to climb up the curve toward that stable peak. Or you can take really heavy elements from the right side and split them apart, moving up toward the peak from the other direction. Either way, you're moving to a more stable state, and that releases all the extra energy. So when you get right down to it, both fusion, which is what powers our sun, and fission, what goes on in nuclear reactors, are really just nature's way of trying to get to that stable, sweet spot at the top of the curve. Two different roads to the same destination. But the story doesn't quite end there. It turns out nuclear stability isn't just a smooth curve. There's one last secret, almost like a cheat code, that gives certain elements an extra surprising boost of stability. And get this, they're literally called magic numbers. Physicists noticed that nuclei with these specific counts of either protons or neutrons were just exceptionally stable. The idea is that, kind of like how electrons form stable shells orbiting the nucleus, the nucleons organize themselves into similar energy shells inside the nucleus. And these magic numbers, they represent a perfectly full, perfectly stable shell.
Let's look at a few. Helium-4 is what they call doubly magic because it has 2 protons and 2 neutrons.
Oxygen-16, same thing. 8 protons and 8 neutrons, both magic numbers. And then you have something like lead-208, with 82 protons and 126 neutrons. Again, both magic numbers. This is why lead is so incredibly stable. It's often the end of the line for long radioactive decay chains.
And this isn't just some abstract theory. It came straight from looking at the evidence, just like our source material here says. Scientists noticed that some elements, like helium-4 and oxygen-16, just had this peculiar stability, and that observation led them to uncover this amazing hidden rule that governs the atom's core. So we started with a simple paradox of why things don't fly apart, and we ended up with missing mass, binding energy, and even magic numbers. It just makes you wonder, doesn't it? With so much power and elegance packed into a space that small, what other secrets are still locked away inside the atom's core?